We're going to work through some different review problems in preparation for the Chapter 2 test. So you can see here in the white we have the height of an object above the ground, and we have a few selected times and their heights, time in seconds, height in feet. So the first question is find the average velocity. So average velocity is like slope. That's going to be s of 6 minus s of 4 all over 6 minus 4, s standing for position, which is oftentimes used. I guess I could have used h here. I probably should have used h. So s of 6 from the table is 70, s of 4 from the table is 90, and then 6 minus 4 is 2. So that's going to be a negative 20 over 2. So that's going to be a negative 10. Remember, velocity can be positive or negative or 0. And this will be given in feet per second. So that's a negative 10 feet per second. So the object is falling at 10 feet per second. So the second question is asking us on a graph. So if we were looking at the graph, what would that average velocity represent? And remember, that's going to be the slope of the line between 2 points that were on that curve. So that is the slope of that's called a secant line, the line between 2 points on the curve. Okay, jumping on to the next one, see if we can do this limit analytically. So to simplify this, we need to get a common denominator. So the limit as h goes to 0 of 2 over 3 plus h minus 2 over 3 all over h. So we're going to multiply top and bottom here by 3 and top and bottom here by 3 plus h. So that's going to be 6, and remember this minus sign distributes. So that'll be 6 minus 2h all over the 3 times 3 plus h, still all over the h. So the 6's cancel each other out, and so this will become now negative 2h over 3 times 3 plus h. This h in the denominator, we're going to divide by that h is to multiply by its reciprocal. And I should say that we're taking this limit as h goes to 0 throughout this problem. They're kind of sticklers about that on the AP exam. You have to keep writing it at each step. So here the h's will cancel. That would have ended the story in our AP prep days, but now we get to go one more step, which is actually kind of fun and satisfying, is we can now, as h goes to 0, that is, we can direct substitute in 0 there, and so we'll get a negative 2 over 3 times 3 is 9, so that is going to be our result, our negative 2/9. So the next one, we have this crazy graph in blue, and we have a bunch of points marked in yellow, and at each of those we want to know, is the derivative at that point on the curve going to be positive, negative, 0, or undefined. So what we'll see is that at A, at this point in time, the slope of the tangent line is going to be falling from left to right, so that is going to have a negative derivative. At B, we have a horizontal tangent, so that means the slope of the tangent line or the derivative will be 0 there. At point C, the curve is rising from left to right, so that's going to be a positive derivative. And what's trying to happen at D is this is trying to show here what we call a vertical tangent. And so at that point, the derivative at a vertical tangent is undefined. What I'm trying to show at point E is that this is coming down kind of like a point, and that's supposed to be a cusp, in which case the derivative does not exist there either. At point F, there's a hole in the graph, and at any discontinuity, the derivative is undefined as well. So the derivative does not exist there. Likewise at G, when you have a jump discontinuity, any discontinuity means the derivative does not exist. At H, we're trying to show it's trying to look like different than at E, that the slope coming in from each side is some positive number. So The derivative does exist on the left and it does exist on the right. It's just that they're not the same derivative. And so that's what we call a corner point, in which case the derivative is also going to be undefined or doesn't exist. And then at point I, this curve, I'm trying to show with the white line, it's approaching an asymptote. But even though that's approaching an asymptote, it's not straight horizontal, so it's not very steep, but there's still going to be a just ever so much positive slope there. It's rising just a little bit as it approaches that asymptote, and so that will still be a positive derivative. I'm going to move to a new screen for a moment. Whoops. I'm going to move to a new screen, and then I'm going to pause. Let's see what we've got here. Some problems down. So here we have a few problems, and I'm asking you to describe the behavior of each function at x equals 3, and those are the functions given in yellow. And your choices are to say that at x equals 3, it is A, differentiable, B, it's a corner point, C, it's a cusp, D, it's a vertical tangent, or E, it is a discontinuity. And so all these have then, all but A are reasons or places where the function would not be differentiable, where the derivative would not exist. So on the first one, if you recognize, that's just a basic parabola, and it's going to have a vertex at x equals 3, but that is perfectly well defined and differentiable. So that's going to be A. It's going to be differentiable there. G, you can see, has our absolute value, and it's going to have its vertex. That pointy part, the corner point there, is going to be at 3, so that is a corner point. That's B. The next one, if you recognize, would factor, the numerator would factor into x minus 3, x plus 3. And since the x minus 3's cancel, that means there's a hole in the graph at x equals 3, and that is going to be a discontinuity E. J of x, if you recognize, is even over odd at x equals 3, and that we have said is going to be a cusp, and so that's going to be C. And at k of x is to the 3/5 power, that's odd over odd, which is going to make it like a cube root. It's going to be a vertical tangent. Now in the green, we see capital T of t is the temperature of a function at an oven t minutes after it is turned on. So T is our temperature, capital T is the temperature, and small t is going to be time. And then we want to explain the meaning of these different things. So at T at 4, capital T of 4 means when we input a time value of 4 minutes, the temperature, capital T, is going to be our degrees. And so we would say this is the temperature of the function, or we would say the temperature of the function is 260 degrees 4 minutes after it's turned on. T inverse, remember we're switching the input and output. So now the input value is going to be our degrees, and our output value is going to be the time. So we would say something like, it will take the oven 6 minutes to reach a temperature of 300 degrees. Now we're back to the original T, capital T. So our input now is again time, and our output now, though, because we have a derivative, it's going to be a rate of change. So this is the rate of change of the temperature in the oven is increasing at 40 degrees per minute 3 minutes after it's turned on. So you could also say that the temperature of the oven is increasing. That's its rate of change. It's increasing because that's a positive 40 3 minutes after it's turned on. Now the next one is a bit of a twister. You got to kind of really think hard to sort this out. So now we're changing input and output values. So our 325 that we're inputting is a temperature. The output that we give here is going to be a time. It's a derivative of that inverse, so it's going to be a change in time per unit of temperature. So it's a change in time per degree. So this is saying that the time is increasing by 0.015 minutes per degree. So that is, it's going to take 0.015 minutes for that temperature to increase a degree when it is 325 degrees. That is challenging. You have to think on that. Now, the next one's going to be challenging too. I've given you a graph here, and the yellow is our f of x. I didn't say what the directions were. So this is f of x, and we're going to try to graph right on here y equals f prime of x, its derivative. And so we have all kinds of twists and turns along here. So first, let's notice that to start with, right in here, that looks to me like it's really close to horizontal, so that's a bit of a judgment call. Do you think that is actually 0 there, or maybe it's just a little bit decreasing, so just a little bit negative, and I think that's open to interpretation. At any rate, as we move from left to right, these are getting steeper and steeper negative. This is supposed to represent a cusp, which is where the tangent line, the slope of the tangent line, is going to fall off the cliff and go to negative infinity. So we're starting at either 0 or something slightly negative, and it's going to fall off the cliff and go to negative infinity as we approach that cusp. Now on the other side over here, now notice this is going to be some kind of a corner point where the derivative is undefined. I'm going to look over here and see that looks positive, maybe even positive, maybe like a +1 or something like that. And then as we work our way right to left and approach that cusp, it's going to take off and go to positive infinity. So I'm going to put an open circle in here, somewhere where I think +1 might lie. And then as we work our way right to left, it's going to blow up and go to positive infinity as we approach that cusp. Now going in the other direction, this part in here looks like a straight line, and it is falling from left to right, maybe pretty close to a 45-degree angle. So I don't know the scaling on the x or y, but if they're the same, that might be like a -1. Now at these endpoints, at the left and right, we have corner points, and so that is going to be undefined. So I'm going to have open circles somewhere around -1, and then the derivative is -1 throughout there. Likewise, once we switch to this other part over here, now we got corner points there, so once again we're going to have the derivatives undefined there, but this looks like a line that's increasing from left to right, and it looks like it's going to be about a slope of 1, so I'm going to put open circles about where I think 1 is and put a horizontal line in there. Then at this part of the graph where we have a horizontal line, the derivative is the slope of that line, which is 0. Because we have corners at each end here, those are going to be places where the derivative is undefined, and it's going to be a little horizontal line segment of 0. Now as I look at this next piece in here, that looks to me a lot like maybe a parabola. And you can see at the bottom here, it's going to have a horizontal tangent, so the derivative is going to be 0 there. It's going to be negative as we approach here, positive there, and the derivative of, say, an x squared is going to be 2x. It's going to be linear. So it's going to be negative to positive. Again, we got corner points on the ends here, so I'm going to go open circle to open circle and go through 0 with a straight line, something like that. Now we move to the next piece, so it looks like it's slightly negative in here, and then it's going to fall off the cliff negative. This is supposed to represent a vertical tangent, which in the derivative is going to be a vertical asymptote. So we have a little bit negative here at that undefined corner point, and it's going to fall off the cliff and go to negative infinity as we approach that vertical tangent. Now on the other side, the slopes go positive and then really steep positive, and then as they work their way to, it looks like a horizontal asymptote, it's going to approach 0, but always be, I'm sorry, that's on negative rather. I said positive. These slopes are negative, so we're going to have a very steep negative, and then as we approach that asymptote, it's going to approach 0, but stay on the negative side of 0, something like that. There's a lot to digest there. I'm going to move to a new screen again, and then I'm going to pause it. screen. Here we go. Okay. So here we have some problems. What I'm saying in the white is describe the behavior of each function at x equals 3. And your choices for answers are, is it differentiable, a corner point, a cusp, a vertical tangent, or a discontinuity? So the first one, f of x equals x minus 3 squared, hopefully you recognize as a parabola. It's got its vertex at 3, and the derivative is 0 there, but it exists. So there we would say it is differentiable. The second one, g of x, we see it's an absolute value, translated 3 to the right. So the vertex, or that corner point there, is going to be at x equals 3, and that means it's going to be a corner point, and it's not differentiable there. The x squared minus 9 over x minus 3, you hopefully can see that the numerator is going to factor into x minus 3, x plus 3. The x minus 3's would cancel, but that's a hole in the graph, which means it is discontinuous there. So the derivative will not exist there. And that's hard to read, but that's supposed to be x minus 3 to the 2/3. Since that is an even over an odd, that's what gives us a cusp. So that is c a cusp, and the derivative does not exist there. And k of x is odd over odd, which, if you remember, like cube root, is a vertical tangent there, and so it also is not differentiable there. Now the next one, the green one, these are tough, so you have to really think about this. Capital T is the temperature in degrees Fahrenheit, and little t is in minutes after the oven was turned on, and explain what these mean. So the first one is just a straightforward capital T of 4 equals 260. The 4 is our input value, is a time in minutes, and the 260 is an output value in degrees Fahrenheit. So this represents the temperature of the oven is 260 degrees 4 minutes after we turn it on. The inverse, remember, is going to switch the role of input and output. So we're inputting a temperature and outputting a time in minutes. So that's saying that it will take about 6 minutes for the temperature to reach 300, or when the temperature is 300 degrees, 6 minutes have elapsed since we turned the oven on. Now we get to the calculus stuff. So now we're back to the original t. So our inputs are again time, and our outputs are again going to be, but since it's a derivative, our output is going to be a rate of change. So it's a rate of change of the temperature per time. So the output value per input value. So this says that the temperature of the oven is changing at 40 degrees per minute, 3 minutes after we've turned it on. Or you could say even more clearly, because it's a positive 40, the temperature of the oven is increasing at 40 degrees per minute, 3 minutes after we've turned it on. Now the next one's really tough, because now we have an inverse and a rate of change. So we have switched the input and output values. So the input value is going to be our temperature in degrees. Our output value is the time in minutes. It's a derivative, so it's a rate of change. So it's the change in minutes per degree of that oven. So what that's saying is, when the oven is 325 degrees, it will take another 0.015 minutes to raise that temperature 1 more degree. So it's a change in time per degree. How much time does it take for the next change in 1 degree of temperature? All right, now looking at the graphs, we have yellow is the original function f of x. We're going to try to graph in blue its derivative, and we have all kinds of issues that we're going to see. So this thing originates over here. This is a bit of a judgment call. You could interpret that as being 0, or you could say maybe it's just slightly negative because that's just decreasing a little. You're open to that. You can make either call there. This is supposed to represent here that this is very steep, kind of like a needle. That's going to be a cusp. And a cusp is going to lead to a vertical asymptote in the derivative. So it's starting somewhere around 0, and then it's going to get really steep in the negative. So it's going to fall off the cliff in the negative, and so our derivative is approaching negative infinity from the left. On the other side, it's going to be very steep positive, going up to, now here another judgment call. Right there is a corner point, so the derivative is going to be undefined. Now just to the left of it, it's slightly positive, so I'm going to say that's going to be about a positive 1. There's my derivative. As I work my way right to left, it's going to get steeper and steeper positive. It's going to go to positive infinity. So in a cusp, you see you get a vertical asymptote and you have different infinities on either side. Now we switch to a piece of the yellow curve here that is a straight line. So its derivative is going to be its slope, which looks like roughly maybe -1. Now you have a corner point on each endpoint. So this little segment, this part of the line that's dropping from left to right, is going to be open on each end because of the corner point. It's undefined there, and the slope of that line looks to be about -1. I don't have any scaling on here, so I'm going to approximate that somewhere in there. Then the next piece of the line looks like a straight line rising from left to right, which means it's going to be a positive slope. Again, we have corners on each end, so I'm going to show that with open circles there and a horizontal line above the x-axis. Say the slope there is positive. The next region here is a horizontal line, which is going to have 0 slope. Corner points on each end are going to make that also have open circles. The next piece looks to me a little bit like a parabola, so it looks like it's got negative slope on the left, a horizontal slope there at the vertex, and then to positive. So the derivative of a parabola, an x squared, would be linear, a straight line. We've got corners on each end of that piece of the parabola, and it's going to be 0 at the vertex. So I'm going to do something like this and make it begin and end with open circles. Next, it's going to be a little bit negative in there. Right in here, somewhere in here, we're supposed to have, that's supposed to look like a vertical tangent. So these slopes are a little bit negative and then falling off the cliff negative. That is going to negative infinity. So from our undefined corner point to a very steep negative in that direction. Now on the other side of that vertical tangent, it's still very steep negative, and then it's going to level off, and it looks like this line is, that yellow line is approaching a horizontal asymptote, which means it's going to approach 0 as a derivative, but maybe always be a little bit decreasing, so a little bit on that negative side. There we go. So I'm going to go to a new panel and see what we've got. Dang it. There. So in the first one here, we have a function that is defined that has all the following properties. So we have that f is decreasing, it is concave up, f of 1 is 4, f prime of 1 is -1/2, and our question is it possible that f of 3 can be equal to 2? Well, let's see, if at 1 we're at 4, our function is going to be right here. We know it's decreasing and concave up, so it's going to have to do something like that. Now, if our derivative is a -1/2 here, that means that if this was a straight line, we would go down 1 over 2. That would make f of 3 equal to 2. And that would be it would have to be a straight line there. But we said this is concave up, which means that if it's concave up, our derivatives must be increasing. So that means even though the derivative, the slope of the tangent line, was -1/2 right at 1, 4, as we move along to the right, this derivative must be increasing, which means that slope is becoming bigger than -1/2, like approaching 0 is going to flatten out. So the only way we could get to f of 3 being 2 would be if we had gone as a straight line along that continued slope of -1/2. So that isn't possible because our derivative must be increasing, and we would have to explain that. Okay? Now, the next one, we're going to explain everything we know about the graph of the derivative. So you're going to have to do something like this and list as many things as you can. So we don't have any markings on the graph, but we can see this looks like a cubic. So one thing that we know is that f prime should be 1 degree less, so it should be a quadratic, should look like a parabola. Now we can see that there are going to be these relative minimum and maximums at these points, which are going to have horizontal tangents. So we know that we're going to have derivatives that are 0, so our derivative should have x-intercepts at those points, but they're not marked. So we need to put markings in so that we can refer to them specifically. So we can say then that f prime is equal to 0 at x equals a and x equals b. So you have to give specifics, not just say generically or generally that it will have 2 x-intercepts or the derivative will be 0 at 2 points. That isn't sufficient. So then we can see that the curve is going to be increasing here and then also increasing there. So that means we can say f prime will be greater than 0, so positive, on the interval, or we can say even greater than or equal to 0 if we want to include that, on that interval from for x less than or equal to a, and then also on that interval for x greater than or equal to b. In a similar fashion, we see that the curve is decreasing on this interval, so we can say that f prime is less than or equal to 0 on that interval from a less than or equal to x less than or equal to b. Notice how it's being specific here because we've introduced this a and b that we can then refer to them there. What else can we say? I think that'll be pretty good for there. Let's add a little bit more. I think we can even get a little bit more detail in there. So on this, let me see if I can indicate there. So we can see that somewhere in here, let me call that point maybe C, that on this interval that the original function is concave down. So since the original function is concave down, that would mean that either the second derivative is negative, or what we could say in terms of the derivative is that f prime of x is increasing on that interval from for x, we'll say strictly less than c, because that's where it's going to be actually increasing. And similarly, to the right here, we see that the original yellow function is concave up, and that means that our derivative, I think I said that wrong. The f prime is going to be, since the f prime is going to be, so this would, since that was, the f double prime is negative, f prime will be decreasing on that interval, because you can see the slope here is going to be positive and then 0 and then negative. So as it goes from positive to negative to 0, that's going to be decreasing. And similarly, f prime will be increasing on the interval for x greater than c. Okay, we'll stop it there.